Okay, so the purpose of this video is to address a particular feature of a sequence, and the feature which we're going to look at is the limit of a sequence. So to assess the limit of a sequence, we are almost certainly going to be given a sequence in general form. So given a sequence simply in the form of a plug and chug expression. And when we talk about a limit of a sequence, what do we talk about? We're talking about the values of the sequence, or what the values of the sequence are approaching as n approaches infinity. So as you go off further and further into your terms, what does the value of your sequence approach? So in practice, as it turns out, the act of computing this limit is very similar to things that you've done previously in Calc 1. Like take, for example, the sequences that are written here below. If you were to take a limit of this expression, this is actually something, well, the limit is n goes to infinity in particular. This is something that could have shown up, I think, on your first test in Calc 1, similar for the other two problems. So now, to sort of bring this into Calc 2 language, when you compute a limit, you know sometimes the limit exists and is a number on the number line. Well, if that is the case, if your limit both exists and is a number on the number line, we say that such a sequence converges. On the other hand, should the limit be plus or minus infinity or not exist, we say such a sequence would diverge. Note, by the way, this notion of convergence and divergence coincides precisely with our notion of convergence and divergence when we were talking about improper integrals. When you evaluate a limit, the limit exists and you get a number on the number line, convergence. When you evaluate a limit and you get plus or minus infinity, or the limit doesn't exist, then you get divergence. So, with this in mind, convergence, divergence, and what the limit of a sequence is, essentially just letting n go to infinity and compute the limit, let's take a look at these three examples. So when you inspect these three examples, you may consider, like, once we write this out here, let me write it out. Limit is n goes to infinity of n squared plus 2 over n. The next one's going to be limit as n goes to infinity of 4 over n, and the next limit as n goes to infinity of n squared plus 2 over 3 minus 4n squared. Now, even as we write these out, and sort of we now bring these sequences and their general forms into the form of a limit to compute, these are basically Calc 1 problems. And in particular, each of these is a rational expression, right? The top one here is in fact a top-heavy rational expression. The middle one here is bottom-heavy. Note the denominator has degree of 1 and the numerator degree 0. So here's an example of a bottom-heavy rational expression. In the last case, we have an equal-heavy rational expression because we've got degree 2 on top and on bottom. And you may recall from Calc 1, when you have a top-heavy rational expression, your limit is either plus or minus infinity or doesn't exist. Well, in fact, whereas in Calc 1, we would have to determine whether or not we got plus infinity or minus infinity. When it comes to Calc 2, we're only concerned with whether or not the sequence converges or diverges. And in this case, this sequence now diverges, because whether you get plus or minus infinity or the limit not existing, you get divergence in either case. What about 4 over n? Well, if you recall bottom-heavy expressions here, the denominator is getting large, and if you take 4 over a very large number, that's going to be practically nothing. In fact, this limit will be equal to 0. And, well, when the limit is 0, note that is a number from the number line. So here, this sequence converges to 0. What about the last one? The last one is an equal-heavy rational expression that we're taking the limit of as n goes to infinity. And if you recall, you simply pluck the leading coefficients from the numerator and denominator. Now, the leading coefficient here in front of the n squared is not expressed, but of course if you don't have a coefficient expressed, you could write it as a 1, and then whenever you pluck the leading coefficients, you simply get negative 1/4. So using our fact about rational expressions and their limits as n goes to infinity from Calc 1, we can compute our limits in each of these cases. In the last case here, note the minus 1/4 that we got is a number from the number line, which means that this sequence converges to minus 1/4. Sweet. Okay, so as you can sort of feel by going through those problems, and as was really explicitly stated, taking the limit of a sequence is using a lot of skills from Calc 1. And so what I'd like to do here is sort of go through some nice rules of thumb to have in mind as you're working limits of sequence. So we discussed in the last example what to do with top-heavy rational expressions, bottom-heavy rational expressions, and equal-heavy rational expressions. So I'm just recalling those for you so that you have them here, easy access to the eye. Another thing to remember is that if you're ever dealing with a constant like 10 or 100 or minus 2.5, if you raise to the 0 power, you get 1, right? E to the 0 power is 1. 10 to the 0 power is 1. Any constant to the 0 power is 1. Something else to think about, which you may not have previously, but is certainly worth mentioning. What if you had a number whose absolute value is less than 1, like say, minus a half or something? What if you took that minus a half and multiplied by itself a bunch of times? What is minus a half of minus a half of minus a half of minus a half? Holy moly, right? That is getting super small, right? Because half the half is really tiny. And half of that is even tinier. In fact, no matter what the constant is, if its absolute value is less than 1, when you multiply it by itself, you're getting something tinier and tinier, and you're getting an ever-decreasing number in absolute value, which is ultimately going to approach 0 in the limiting case. Now, what if, on the other hand, you had a constant which was greater than 1 in absolute value? Well, here, when you multiply it by itself, you'd get something bigger and bigger and bigger. In fact, it's possible for this limit to not exist if you'd be multiplying by a negative number, but nonetheless, whether you're multiplying by a positive number or a negative number, if the number is bigger than 1 in absolute value, you're getting something bigger and bigger and bigger without bound, which is ultimately going to, whether it's plus or minus infinity or not existing, going to lead to a divergent limit in our convergent and divergent language. All right, last fact to keep in mind is L'Hopital's rule. So if you recall, when you're ever evaluating a limit, if you get plus or minus infinity over plus or minus infinity or 0 over 0, you can, well, since those forms are indeterminate, you can use L'Hopital to have a chance of maybe getting something that is determinable. And, well, how do you use L'Hopital's rule? You simply take the derivative of the numerator and the derivative of the denominator and reevaluate the limit. I'd like to make one caveat with this, because remember, there are some cases where you have a product and L'Hopital's rule applies, and that's when you have a product of 0 times plus or minus infinity. In this case, you simply form this product in the expression, in a quotient expression, write it as a fraction essentially, and then you can apply L'Hopital's rule. So if you ever get 0 times plus or minus infinity, we simply rewrite as a fraction and then work the problem. Okay, so with these facts in mind, let's proceed down to these 4 examples below, and let's determine if these sequences converge or diverge. Should they converge, we can actually say exactly what they converge to. So let's take a look at this limit. This one is, the limit is n goes to infinity of 4 raised to the minus 9 over square root n power. Now, when you look at that minus 9 over square root n, that is sort of like a rational expression. This is a bottom-heavy rational expression. There's more power of n in the denominator than there is in the numerator. And as n gets big, the denominator is going to get big. As the denominator gets big, this bottom-heavy expression is going to go to 0. So ultimately, the limit is going to be 4 to the 0. Well, 4 to the 0, any number that's a constant to the 0th power, is simply going to be 1. So this limit converges. In particular, it converges to 1. Because remember, anytime you take a limit and you get a number off the number line, well, then you have a convergent limit, and you will converge to whatever that value is. Okay, what about the limit as n goes to infinity of 1.3 to the n? Well, here we're taking 1.3 times itself a bunch of times. And when you take 1.3 times itself twice, well, hell, you get 30% more than you started with. And when you multiply by 1.3 again, you get 30% more than you had. And you multiply by 1.3 again, you get 30% more than you had. And this is going to cause the values that are associated with this expression, with this general term, to get bigger and bigger and bigger without bound. In fact, this is precisely the case that we were discussing above. When you have a number, absolute value greater than 1, which is being multiplied by itself a bunch of times, this is going to be plus or minus infinity, or won't exist. In this case, actually, it's going to be plus infinity, but frankly, we're not concerned with whether it's plus infinity or minus infinity or doesn't exist. All we're concerned about is that the sequence diverges. So this sequence diverges. Why? Because when you evaluate the limit, you either get plus or minus infinity, or the limit doesn't exist. Okay, what about this third example? This third example is the limit as n goes to infinity of 7 to the n over 8 to the n. What can we do here? Well, note both numerator and denominator are being raised to the nth power. If we simply rewrote this, we could rewrite it as limit as n goes to infinity of 7/8 to the n. And if we did that, well, then we could simply apply the fact that since 7/8 is less than 1 in absolute value, when you multiply it by itself, you get something smaller, and multiply it by itself again, you get something smaller. And the more and more you multiply by itself, you're going to get a value that limits to 0 in ever decreasing absolute value, ultimately limiting to 0. So here, since the limit is a value off the number line, this limit converges, and in particular converges to 0. Okay, what about this last one? This last one is the limit as n goes to infinity of n squared e to the minus 3n. Note that first term evaluates to infinity, and that second term, since e to the negative 3n power is like e divided by itself 3n times, well, that ultimately, as n goes to infinity, is going to equal 0. This is lots of powers of e in the denominator in effect. And so when you take this expression, which it turns out to be infinity times 0, it might trigger a memory in your mind of something that was recently discussed. In particular, this is the product form of L'Hopital's rule. If we rewrite this product as a quotient, we can then apply L'Hopital, and that's exactly what we're going to do. We're going to take the limit as n goes to infinity, keep the n squared upstairs, bring the e downstairs, e to the 3n. And now, this expression is of the form not infinity times 0, but now this is in the form infinity over infinity. And what does that mean? That means we can apply L'Hopital's rule. So applying L'Hopital's rule, we'll take the derivative upstairs and get 2n. We'll take the derivative downstairs using the chain rule and get 3 e to the 3n, or e to the 3n times 3. Now, this still evaluates to infinity over infinity, which is not great, but it's also not the end of the world, because what this means is we have an expression that again could have L'Hopital applied, and if we apply L'Hopital one more time, we will get the limit as n goes to infinity of 2 over. Downstairs we'll have 9e to the 3n, and well, upstairs is now 2, downstairs is getting very big, and 2 over a very big number is 0. So this limit also converges to 0, which I say converges because the limit exists and it's a number off the number line. So long story short, given the general term of a particular sequence, you can use your knowledge of these variety of facts that relate to what you've studied in Calc 1, and you can ultimately leverage your Calc 1 understanding of limits to compute the limit of the sequence that you've been given.